Yeah, thanks. Thanks a lot for reminding me. So yeah, with that, I'd like to get started. And I guess I do have a question for you guys, and that's like, how much of RNNs has Bhiksha covered in class? Has he
We
touched
just
on
talked about
LSTMs?
LSTM.
Sorry, go ahead.
LSTM. So we were just talking about we just completed the introduction of regular vanilla RNN, and then talked about a bit about LSTM.
Okay, okay, cool. So I hope you guys are familiar with RNNs, and I guess that's a good place to start talking about the CTC laws and where we might need it. Uh, so let's say we have a sequence classification problem, uh, or a sequence to sequence prediction problem in some sense. So what would be a good example here? Um, so anyways, let's say I have a sequence of tokens going in my RNN. Let's say we have a language model. Did Bhiksha cover language models in class yet?
I don't think so.
Okay, so basically what language models are supposed to do is, let's say if I'm sending in the letter, the words, the letters of the word sunny, and this is again going through an RNN-like network. So what a language model is supposed to do is it's supposed to be producing the letters of the word itself, but shifted by one. You'll be dealing with a similar problem, I think, in homework 4, part 1, but that's a little far off right now. So this is more like a sequence to sequence prediction problem where you have you have an output at every time step, and you know what the output at every time step is supposed to be. So it's a relatively easy problem to solve from the perspective of modeling it with a loss function. You could use something as simple as a cross entropy loss function and solve this. The the difficulty comes, and that's precisely because you know that every time step what output label you want. And for this time step, it's going to be, you know, that your label should be S. At the next time step, you know, the label should be U, and so on. Now that's a problem where at the input you have ti time steps, and at the output you have tm time steps, t out time steps, and t out is equal to t input. Now, there are scenarios where that is not always going to be the case, and the most trivial scenario, or the most common scenario, and something that you're going to use in homework 3 part 2, is speech to text transcription or speech to phonemes transcription. Speech to phonemes transcription is something you've done in homework 1 part 2. And in homework 1 part 2, we kind of, what we did was we had speech frames as input, and for each frame we had an output phoneme corresponding to the frame. Now, if instead of, and like just if you think about a person who's labeling that, it is a really difficult task of labeling each frame of the speech as a particular phoneme. And sometimes we're directly uh, looking to, and for that kind of problem, what we also need is that at every time step, so instead of now a word going in, we have uh, a speech signal going in the RNN, and at every time step, at every time step of the speech signal, somebody needs to set and label what the phoneme coming out of the network is at that time step, and that usually um, is not how people label things. It's very hard to set and label every frame of the speech, and the most common way of labeling speech is that I say something and somebody gives me a text transcript of what I've said. Now, what that lacks is a timing information as to where a word starts, where a character that I said starts, and where a character that I said ends, and what and the speech in time does not correspond in a one-to-one manner to the label of the word. So, for example, here in these three time steps, I'm trying to say sunny again, and in the first three time steps, I've been able to say uh, or I've been able to produce the sound corresponding to the word S. In the second two time steps, I've been able to produce the sound corresponding to the uh, letters U and so on. So ideally, what we'd want is that our somebody who's labeling for us is able to generate is able to label in such a way that at the end of three frames of input of speech, uh, they're able to tell us that at the third uh, frame, I've completed the sound for the letter S, and that's when the prediction S should come out. And the at the end of two more frames of speech I've sent, I've been able to say the sound for corresponding to the letter U, and the letter U should come out, and so on. So this is like kind of the next best scenario where we don't have one-to-one correspondence between input and output, but somebody has given us timing information. So again, in this scenario, Ti is technically T input is not equal to T output in terms of the sheer number of the inputs that go in and outputs that are produced. But we do have timing information, and this problem again we can solve using our old friend cross entropy loss, and it's um, and I mean, like, if we look under the hood, it's just like we have a vocabulary, and uh like we'll have like a log softmax uh, score for each word, each token in our vocabulary, and then we'll calculate the loss at each time step and sum it up. So that kind of happens when we do have timing information of a sequence to sequence prediction model, sequence to sequence prediction problem, where the we can say the input sequence and the output sequence are time synchronous, but they're not equal in length and they're not regular. That's something that we still can do. But again, having such a scenario is also a little unrealistic for generating for people who are labeling. And what we usually have is just a time, a speech signal in time. So this is input speech, and for that somebody has just labeled today is a sunny day. So we have speech input and we have a text transcript of the speech input with no other information as to at what portion of the speech the letter T corresponds to, what portion of the speech the letter O corresponds to. We don't have that information. All we have is the speech input and the text transcript, and from that we have to, in some sense, what's learn how to learn learn how to generate speech to text transcriptions in this form. And that's kind of what makes the problem difficult, not having an output at each time step, not knowing what the output at each input time step of the speech signal would be. And uh, that's the place where we use the CTC loss function. So that was an introduction to CTC, connectionist temporal classification. Uh, I have a question here which says, how to define the loss for the letters? Is it like S goes to S with zero loss? All the other outputs are with one loss. Yeah, so it's something similar to using LSTMs. Sorry, did I say LSTM? Something similar to using a cross entropy loss. So, or it's exactly like a cross entropy loss. You have a logit where you have a bunch of you have all the tokens in your vocabulary. So let's say this is SUNAYD, and so on. And you'll have a softmax score for each of them. So 0 0.1, 0 0.03, 0 0.4, something like this. And then you'll take cross entropy uh, loss for the entire logit, and that's what your loss would be in a scenario where you have timing information. So does that answer your question, Zilan? Cool. But yeah, so that was an introduction to CTC loss and where we use it and why we use it. So, and hopefully this made sense considering you've looked at RNNs. But if anyone has any questions as to the motivation behind CTC loss, how it's done and the math behind it, it's something I'm not going to go into, because one, it's going to take a lot of time to Bhiksha spends a lot of time on it. So I think I'm just going to show you how to use that in code. But I'll be very happy to answer any questions that anybody has, either about RNNs, LSTMs, or why and where we use CTC laws.
So
So,
I just have
all
a
right, go
simple
ahead.
question. So I
Mhm.
guess C2C loss is basically to take into account the missing time information
Right.
and tries to match the speech and the text.
Yes, yes. We try to take into account the missing time information, and the way we try to do it in CTC is that we're trying to guess, in some sense, alignments of our predicted speech transcription and the actual speech transcription. And in in a way, we're kind of taking an expectation in the CTC laws over uh, all possible alignments, and that's what we're using. That's against that we're calculating the loss. And yeah, but that's something that Bhiksha would go into detail. But yeah, that's the problem that we're trying to solve, and in some sense, trying to align what the network generates and the actual transcripts. And given that the timing information is missing.
Got it. Maybe the CTC loss will also give us the alignment information so that we can actually segment the speech into individual words.
Yeah, I mean, so it's different while training and testing, but during training time and inference time. And in inference time, let's say you're able to train the network with missing timing information. To do that, you use CTC loss. And at inference time, you use something that is going to be very similar to a beam search. So a beam search is something that Charles will go over after this, but it's basically at all time steps. Let's say the beam is of size one, that at all time steps you're taking into account the the you're taking the highest probability logic. But I think it's a good question. I'll maybe go through it once quickly of how we in terms of practice how this is done. So for example, I have my RNN that looks something like this. uh, so again, speech is going in, um, and the word what comes out at time step, uh, as let's say at time step 2, I've converted the amount of speech that corresponds to the letter S. Then at time step 4, I've converted what corresponds to U. At time step 5, I've completed N. 6, I've again completed N. Um, and after another 3 time steps, I've completed the letter Y, and all this is speech input. Um, so the way that we're kind of what we're doing is we're generating outputs at every time step. So we're generating a logic at every time step. So again, as I showed over here, a logic like this is being generated at every time step. And so we have a softmax score for every word in every letter in our vocabulary. And even at the first time step, we're going to be choosing S. At the second time step, we're going to be choosing U. At the third time step, we're going to be choosing N. And at these time steps, we're going to be choosing, so just changing colors. We're choosing the logic corresponding to Y, something like this. Now the task at inference time. So the task at inference time becomes to be able to reduce this produced transcript into the word sunny. And to do that, we do something as simple as reducing repetitions. Um, so we have SSUU, 3 N's and 3 Y's. We're going to be reducing all the repetitions so that what we generate from this is remove all the repetitions. So you'd end up with SUNY. Now, just removing all the repetitions, here's the problem here is that what if there are letters, what if we want to deal with something, a word like sunny, where N needs to be repeated twice, and if we're just removing all repetitions, we are not dealing with letters that are repeated. So in order to do that, we kind of introduce a blank symbol there. So I add a symbol called blank in in my vocabulary, and have a logic softmax score corresponding to that as well. And a blank is also generated. Uh, a blank should be generated at this point. So that kind of tells that these two n's corresponded to one n, and I should reduce them. but this n was independent, and hence my output should be sunny with two n's and not sunny with one n. And this is kind of the decoding problem that Charles will go through in the second half of the recitation. But yeah, I hope this made sense. If not, feel free to ask any questions.
Couldn't we have put blank not statements, but blank characters instead of repeating characters and then just filtering them out? Instead of creating a whole new decoding problem for ourselves.
Wouldn't so you're saying that we had like blanks, 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 blanks.
Yeah, like how exactly are we coming up with the green stuff?
So the thing
Is
is
it just,
that
yeah.
Sorry, go ahead.
I was just gonna ask, is it just like partial predictions that we have that we say it's an S, or?
Yeah, so we do have a logic being produced at each time step, and we're taking the maximum, uh, the logic corresponding or the token corresponding to the highest softmax score. The thing is, this is how we're training the network, where the at training time the network is learning to produce a blank only at the uh, in some sense the word boundary, the token boundary at which and this is only being looked at if there is a repetition. uh, and in a sense we're trying to produce, so blank is only being used to differentiate between um, and this again goes back to the thing that we don't know the timing information. So if we had to generate blanks here, we would have had to know that the S letter gets completed after two frame inputs and the Y letter gets completed after three frame inputs, and we want to generate two blanks and a Y. So if we had that timing information, we would have we would have done that. In fact, we would have never done this entire thing. We would have only generated the blue ones. But because we don't know that, we're generating outputs at every point. And then during training, we're trying to incorporate the blank symbol in a way that if there are repeated symbols, like in the case of sunny, there is a blank introduced before before them. So the answer to what you, I mean, I think it was a good question to have, considering the limited number of things I've explained. But the reason behind it is that we don't have timing information to generate blank symbols and generate just the the blue letters at the right time step. And how it's done is something Bhiksha will go through. So any other questions? So I guess if not, I like to I like to wait just to extract questions out of people. So I hope nobody got bored in the pauses that happen in between. But if there are any questions, feel free to interrupt me. If not, I'll show you a code demo of CTC loss and then hand it over to Charles for the decoding problem. Cool. So this is a very simple toy problem for running CTC loss or using CTC loss. The data here the data here is the word and the pronunciations of the words. So this is a different kind of problem corresponding to what we discussed. This is word as input and their phonemes as output, as if somebody, it's the phoneme, the sequence phonemes corresponds to if somebody was saying those words. And what you will have in homework 3 part 2 is like, instead of the word, textual word as input, you'll have speech inputs. But yeah, so this is our training data where we have word to phoneme mapping. And this is our, I guess, test example, Einst. Should be Einstein. Anyways, and this is, I think this is a vocabulary of words, and we have a blank symbol here, and again, that corresponds to the blank I was talking about. What you have to do in RNNs is to, so this is just converting, so assigning an index to everything in our vocabulary. So phonemes uh, are assigned an index. So, and every word is then written as a transcription of the our vocabulary, and then we have a very simplistic model that we train using the CTC loss. So the CTC loss takes 4 arguments, the laws that are produced at each time step, the target symbols, the input lengths, and the target lengths. So some things you don't need to care about right now, but these are the things you'll use in homework 3 and homework 4 are packed sequences and packed sequences, what these are. And essentially what they correspond to is that if you take a batch and there are different sequences in a batch, for example, C, set, sit, and cite, these 4 form a batch. They don't have the same sequence size in time. So what a batch does and what packed sequence does is it pads the uh, remaining. So it will pad. You will actually pad the C set in with zeros, and what packing does is in some sense it will also arrange them in a certain order, and it will create. So I guess it's difficult to explain. It'll optimize it such that at every time step, it's picking one word each from each of the inputs. But don't need to care about that right now. You can get into it in much more detail in one of the homework 3 boot camps. But yeah, and it's pretty simple. The model, instead of using the cross entropy loss, you're just using the CTC loss. The important thing to know here is that when you're creating your vocabulary, the index 0 is reserved for the blank. So your vocabulary should start from 1. And then note that the RNNs are also padding. So your padding index should not be the same as your blank index, because blank and pads are different things. So you should take care of this when you're creating your vocabulary. And when, as I said, there are 4 sequences in a batch and 3 have different lengths. So you're going to pad C, sit, and set with a 0 because there's nothing there. But that padding index has to be different from your blank index. And here index 0 is reserved for blank. So you need to create a vocabulary and then have one a special index corresponding to pad. And then it's pretty straightforward. You can just use it as it is. This is during training time, and during inference time, you're kind of decoding. Uh, and to do that, we have the CTC beam decoder. And there are a bunch of arguments here. For example, the beam width is an important one. I guess what beam search does is something that Charles will go through. But once he does, and once you understand CTC and why you need beam search, this kind of becomes trivial to use. Again, the catch or the thing to take care of here as well is to make sure that you're taking care of the blank symbol and the padding index, and both should be different. So yeah, this was the very simple model to use CTC loss. Um, if you guys have any questions up till now in the code or the CTC loss, uh, feel free to ask. Otherwise, I'll hand it over to Charles for the decoding
I have a
problem.
question. So,
Mhm.
when you in this case, when you see repeated formies, you have to add a blank. Right? You have to preprocess it.
No, you won't have to do it. CTC loss would be doing it for you,
Oh, okay.
but in general, you have to add a blank if you were implementing it on your own. And it's a little more complicated than that. Blanks are being added, but then um, you're also picking a subset of the vocabulary that corresponds to your training labels. Bhiksha will go through it in detail, but in general, for the homework at least, you don't have to add blanks. CTC loss implementation of PyTorch will take care of it. So you just need to
I
pad
see.
it at the end and make sure to reserve index 0 for the blank, which the function
Oh,
implementation will take care of.
so index 0 always corresponds to the special.
Yeah,
Blank.
corresponds to the blank. Yeah.
Also, why is CTC decode a separate package instead of being part of PyTorch?
Uh, I it's part of PyTorch.
I mean the decode.
Oh, that, yeah. I don't know. It was released much later. Actually, uh, if you had taken this course 3 semesters ago, you wouldn't have had this package. So it was released 1.5 years ago. It's I don't know why it's not a part of PyTorch. Yeah, yeah. I have no idea. Some awesome TA found this some time back, and now we've been using it. Maybe there's something out now. I haven't checked, but if you do end up finding it, please share it with the rest of the class. Cool. So any other questions that anyone might have? Okay, awesome. So I'll hand it over to Charles now, who look at beam search and CTC decoding. Hey Charles, you there?
Sorry, can you hear me, everybody?
Yeah.
Okay. First and first is that CTC loss would be part of homework 3, part 1. So, like Akshat said, we'll be using CTC loss in part 2. I mean, in the part 2, homework 3, part 2. But for homework 3, part 1, we'll actually be implementing CTC loss from scratch. So I think it's going to be something you should look forward to. So, and this recitation basically is not to give you everything you need for implementing CTC loss. It's just to introduce you to the concept. Big Shah personally would make sure that you understand CTC loss. Actually, Big Shah has like the best CTC loss lecture on the planet, kind of. So I think Bisha will do everything as within his power to help you all understand CTC laws. But I just wanted to point it out so that you look forward to the class and make sure you understand everything, because you will be implementing CTC laws as homework 3 part 1, and it's kind of time consuming. So just as a heads up and something you should prepare for. Okay, so I'll go ahead to share my screen. So can you all see my screen, please?
Yeah.
Okay. So from Akshat's talk about CTC, basically you have this kind of graph. It's easy to construct your graph this way because you have targets. So let's say for this particular input instance, you have a target of BII F, right? Like BEE F of. So it's very easy to construct a graph this way. You can basically introduce blanks in between each of these, and during training, it has a way of knowing the skip connections, how to skip and how to skip, and how to merge BII, and I mean make it unique and all. But like I said, we wouldn't be going deep. And this is something that you would see very much on this slide, because it was actually, I mean, in the lecture, this was actually brought out from the lecture itself. So I think you should look forward to this. But we have this, and now we would go to, okay, I think actually I talked about the training procedure. So now the question is, how do we decode at test time? It's easy to, I mean, decode here because, like I said, we have the target already. It's easy to introduce blanks at this particular at this particular point. So it's always introduce blanks before each character or each phoneme in this case, and after and at the last. So, but I mean, when it comes to, okay, so first, okay, so at this point, for our doing inference, we actually don't have labels, right? So we would not be able to do something like what we did here, because we could actually do this because we knew the labels, and we knew how we could kind of try to collab things and everything. This is like a Viterbi algorithm, of course, forward backward Viterbi algorithm, which you would talk about in the class. So this particular one, we actually don't know. This actually is a list of all the phonemes we have in our example. Let me just say in our example, or in our problem. Yeah. So these are all the test cases. I mean, these are all the phonemes we have, right? But we don't know how we need to combine them. We don't know if we need to have, if at this particular point we need to decode starting from B to D to E to, I mean, to A to E to F and to G. I mean, we don't know. We just have a bunch of these, right? So, but the point is, how do we know how to decode this particular example? How do we know how to, like, which one comes first, which one we're going to collapse, which one had the repeated symbol? I mean, these are just everything. We don't even know if we have double B. We don't even know if we have double D. We don't even know if we have like 3 of these. I mean, we don't know anything. We just know that these are everything we have, and we're giving bunch of inputs. Yeah. So this is actually why we need decoding, to be able to decode meaning from this list of so it's like having like a list of alphabets A to Z, right? So I mean, having A to Z does not really mean anything, right? You have to know how to you have to like coin out meaning from A to Z to be able to spell maybe the word forward, or to be able to decode the word output out of A to Z, or to be able to decode the word D out of A to Z. So that's basically what we have here. So we just have this given to us, but we don't actually know how to decode during test time because we don't have labels, of course. That's why. So that's actually why we don't know. So returning to the decoding problem, actually there is like an easy way we can actually decode, which is actually the greedy decode. And what greedy decode simply means is at each time step, right, we probably just choose. So this is the time step. We probably just choose the highest probability here. So the highest probability here could be R, and we go to the next time step and choose the next high probability. Maybe it's also still R. Then in this time step, it comes down to E here. And of course, here the IX is. So basically, so we could just do that and of course go over. But as you must have observed, this is actually very suboptimal because it would not give us the decode. I mean, yeah, it could not give us, it would actually not give us the actual result we want because it's a greedy search. You're just picking the marks. Though you must have, you trust your model to be able to predict something good, but irrespective, greedy search would not give you an optimal solution. And if we want to, we would also say, I mean, if you remember, we would see that the objective of decoding, for example, right, is to produce the most likely asynchronous symbol sequence, right, at every, I mean, spanning our data or our inputs rather, right? So the actual method that we're going to use or that we'll try to talk about here is not the greedy method because, like we said, it's not suboptimal. I mean, yeah, it's not really optimal. So we'd actually talk about the other kind of decoding. So, and what this kind of decoding, you actually find all the decodings, right, and pick the most likelihood. Ashad mentioned something about MLE, which is maximum likelihood estimation. Yeah, so this actually works here. So basically, you just just do like a run through of all the decodings you have in your input, like every possible combination, and pick out the maximum or pick out the most likely or pick out the best. But unfortunately, I'm sure that you must have gotten a hint already that there is going to be like so many computations involved. I mean, it's going to be exponential because for each in this case, for this you have to do a combination of everything. For this you have to do a combination of everything, and I mean, so you just have to combine everything to pick our solution. In this case, we have 8. It could be easy. I mean, but in a typical problem, we have very large graph, very large graph exactly. So it's actually so unfortunately we cannot do this. We can't just find all the decodings and pick the best. In as much as that is actually what is theoretically possible or theoretically better to do. So what's the solution? Solution is actually to organize all possible symbol sequence as a symmetry. So what is symmetry? It's basically this. So it's a tree where, first of all, let's assume that from now to the end of this presentation, we'll be having, okay, sorry, I want to say something that in case you have any question as I'm talking, you can interrupt or you can write it in the chat. I think Akshat would answer, or if I see that, I can also answer it. So feel free to interrupt me, of course, at any point. Okay, so at this point, we want to assume that we have just 3 symbols in this problem. Here we had, of course, 1, 2, 3, 4, 5, 6, 7. Here we had 7, but that would be too hard to explain. So we just want something simple. So we have 2. As Akshat pointed out in the code, we will start with a blank, and I think he spoke about why would definitely need a blank. So basically, we have a blank, S1 and S2 for our problem. So a symmetry is like a tree whereby every symbol connects to every other symbol other than itself. So if you can see this, the blank connects to S1, the blank connects to S2, S1 connects to a blank, it doesn't connect to itself. S1 also connects to S2, it doesn't connect to itself. Then it also connects to a blank, which, okay, basically the third point is trying to say S1 can only connect to X1. only going through a blank. So you cannot go directly from S1 to S1 because in decoding, we're trying to avoid repetition. So there's something called repetition versus extension, right? So Akshat mentioned, he gave example of Sunny, SUNNY. And yeah, so let's imagine that was doing inference. We're supposed to infer SUNNY. So now what's the difference between repetition and extension, right? For extension, you would have an N here. So let's say coming from some part of this tree, we had SU, yeah. So at this point, you have an N here. And if you have an N here, or if it connects directly to an N, what happens during decoding is going to merge them and become just one N, right? But like actually mentioned, you introduce a blank in between, right? So definitely during decoding, S1 would remain. This blank would definitely go, and S1 will remain. So that's why we can actually have SU. Imagine this is N, and imagine this is N. That's why like double N will actually remain in our final output. So I hope you understand or understood what I just said. And of course, each node represents a unique symbol sequence. So at this point, or at any node at all, so maybe at this node, you have a unique symbol sequence, blank to S1 to blank to S1, blank to, so it's always unique and not something duplicate. So we have, for this particular tree, we have a graph for it, and basically don't be overwhelmed by this. It's actually not so difficult. It's actually not difficult at all if you follow it very well or carefully. So basically, what we have here on the x-axis are just the time instance for the input. So this is instance one. I mean time one, time two, time three, or 0, 1, 2, 3, 4, 5, depending on how you can understand it. And what we have here is just a flattened form of this from top to bottom. So you can see we start with a blank S1 and S2 and all going and everything. You can see S1 connects to a blank. So you see a blank S1 and S2, then S1 here connects to the next blank. You can see it here. So S1 connects to the next blank as S1 connected to this blank here. Then S1 also connected to S2. We have something saying S1 connected to S2. It can't connect to this one here because this would probably be connecting S1 here to S2. So it's connecting to the next S2. So that's why we have S2 here. So it's basically just a flattened form of this. And these are just parts. These are just probabilities, right? So we are saying if this particular decode or forward pass, like you would understand from your Viterbi algorithm, kind of forward, backward, forward pass. So you could say what's the probability of this part, right? A blank S1, a blank, a blank, a blank, a blank, right? This is the probability, the alpha probability, or just all blanks. This is the probability of this is the probability. And the actual decoding is actually that you pick the maximum here. So you select the symbol sequence with the largest alpha. This is basically what beam decoding does actually, right? So you have, you compose a tree like this, and you try to compose like the parts to which I mean this kind of, you kind of like map out the parts, and you pick the probability at this final instance. The maximum one will give you the best part, so that would actually be your particular decoding. Let's say it's let's say we're trying to decode the word decoding, right? So let's say this part gives you the largest. This one here gives you the largest. So basically this will amount to decoding, right? Yep. So even though this is, like I said, this is basically what beam decoding does. So even though this is theoretically correct, and mark this word, even if it's theoretically correct, So this is actually the theoretically correct CTC decoder. There's nothing more than this. But in practice, this graph gets exponentially large, like very quickly. So doing this is something that's not really practical because from a big graph, you can't take all the parts and get the largest one. I mean, it's too big, so you can't do that. So to prevent that, there's a strategy called pruning, right? Which Akshat mentioned, mentioned something about pruning when he spoke about choosing the largest k output from your largest k probabilities, right? Yeah. So basically, but we'll talk about what pruning is in the subsequent slide. So what pruning does is actually helps, number one, to keep the size of the graph manageable. Secondly, the computation. It helps to keep the computation manageable also. Sorry if I'm going too fast. You can, like I said, you can always call me back or try to ask something. So that brings us to the algorithm that we'll be using and the strategy we'll be using, which is actually the beam search. And basically what beam search is beam search is trying to say at this particular point, give me the largest. So at this particular point, at this particular time instance, give me all possible combination, right? So I don't know if I can use this. So this might not be the most appropriate figure to use, but just bear with me because I mean it could work for the first time step, but the other time step it might not work. But I think if you follow it, you would understand what I'm trying to say. So for this part, let's say initially this was what came into your this was what your model predicted that you're trying to decode, like everything here, right? So what beam search is saying, at this particular point, right, you consider all combinations. So now at this particular instance, everything here is a combination. Like we just have all of these, right? Now there's something called the beam width, which Akshat also spoke about, if you remember. So there's also like a beam width, which says how many of these do you want to keep, right? How many of these inputs, output or input? Well, inputs are decoder, but output from a model. But how many do you want to keep, right? So let's imagine our beam size K is actually 3. So what beam search is you keep the highest 3 here, the highest probability here. You keep those 3. Then, so okay, let's imagine our highest probabilities are the first one, the third one, which is D, and the fourth one, which is E. So now from this time step, this is what we are doing. We're only keeping R. Is this a picture? Okay. We're only keeping R, we're keeping D, and we're keeping, is this A or E? No, I think this is A. So we are keeping A, right? The rest would discard, and that's what pruning does. Pruning basically discards the rest. Just pick this best one. Now for each of these best one, so don't forget we have R, D, and A. Now for each of these first one, we do all possible combination of everything again. So we have R mapping to R, we have R mapping to B, we have R mapping to D, we have R mapping to E, we have R mapping to everything. I mean, all possible combinations. And we also have D mapping to everything here. And we also have A mapping to everything here, right? So this will give us, so this is 3, this is 1, 2, 3, 4, 5, 6, 7. So this will give us 3 times 7 possibilities in our next time instance. I don't know if you understand it. Okay, I hope you do. But this will give us 3 times 7 possibilities. Then because our beam width is 3, what happens is we pick the top 3 from, not from 7, but from the whole 21. So yeah, it's 3 times. So we have this possibility for this possibility. So it's just 21. So we pick the best 3 out of the whole 21. Then those three will also again map out to all the symbols and everything. Of course, would get it. It's very intuitive, actually very easy. So it's easy to understand. You can actually see, I think Andrew Ng actually does something like an overview of what I just explained, but it's easy to understand. If you don't understand it here, you can actually check it out. But that's basically what beam search does. And of course, it uses the beam width, like I said, which is just an integer that determines what part to be considered. A symbol set, which are the set of all the symbols we're talking about. This, of course, without the blank. I mean, you definitely, yeah, without the blank. I mean, we're talking about inputs to our beam search now, right? So without the blank, and y is an array of probabilities of length of symbols plus 1 times t. And you can see it here. Y is basically length of all the symbols plus 1, which is our blank. I think Achat pointed it out. We always introduce blank to our phonemes, to our symbols, like we saw in the notebook. Then by the sequence, I mean the time steps that we have. That's basically what our graph takes. So before I go into the algorithm proper, because this is actually important, because basically homework 3 part 1 would want us to implement a beam search that it's actually what we have here. So you don't need to go to any external resource to know what a beam search is. I mean, following this pseudocode is actually what you're expected to do, but I think it's okay you still understand pseudocode, because this is pseudocode and not Python or not Java or not JavaScript. So before I go into the pseudocode itself or the algorithm itself, does anybody have any question from the previous slide? Sorry. Any question? Should I go on? Sorry, can someone say okay, so there's a yes. Okay, yeah, I can definitely go on, but I think I should get another yes if everything I've said so far like makes sense and was clear. Was that a yes? Oh, okay. Oh, okay. All right, thanks. Okay, so we go back. I mean, we go to the algorithm now. So the first step of the algorithm is, first of all, there are two containers. I like to call them container. Okay, so for this tutorial, I might call some things containers. I might call some things list. I might call some things whatever. But I don't think you should really consider what I was saying, because, like I said, this is a pseudocode, and this is not a particular. This is not like telling you, okay, Python, and for Python is going to be the implementation. If you understand it, you find what the appropriate data structure should be for each of the variable. But basically, I mean, a data storage just like a data structure is more like a data storage, right? So that's why I'm calling them containers or list or set or dictionary. I mean, yeah. So this algorithm is pretty perfect. I mean, so once you understand it, you would really know what you're supposed to do. Okay, so the first thing is, let me go here. Okay, so just a run through of the whole algorithm. The first thing to do is to initialize your path, right? Because we are working with decoding path, right? So we need to initialize our path. And basically, this is just you initialize it from the first time step, right? So everything in the first time step becomes like your initial path. From time step 1 to t, which is the end of the last time sequence. That's the time sequence. The last, yeah, time sequence. Yeah, from 1, you first of all you prune. So basically, if you remember what I said from the example I gave, from the very first time you prune, you have your first set of 3. If you are choosing beam width as 3, so you have your first set of 3. Then you move to the next step. Yeah. So this is actually what the pruning does. So these are all, this is not all, I mean, this is the high level of everything, but as you can see, we have functions here or method. Yeah, functions, we have them here that would have to implement and go through. So we have, first of all, initialize path, and like I just mentioned it. Then we prune, of course. Then we extend parts with blanks. And next thing, we extend parts with symbols. And what we do at the end of the day, we merge identical parts because what identical part is trying to say is, don't forget, we're trying to decode, right? So if you have like ABC blank and we have ABC in our container, let me use the word container. So if you have ABC blank and ABC, I mean, both of them are the same thing. So in our container, we just want to merge them, merge like the scores for both together. So that's basically what this does. Then of course, because from here, because we've been pruning, we've been getting the best of all, then it's very easy to just pick the argmax of the final part score from the merge. And this will actually give us the best score. And this is what you would return, or you would submit, or you would, if it's to cargo, this is what you submit to cargo. If it's for homework one, this is what you submit as your return statement, basically. So let's go. Before that, there are two variables here. One is the part score, and the other is blank part score. I'd like to point out that part score is basically a container that stores or a list that stores the scores for parts that ends with a symbol, right? And the blank part score are parts that ends with a blank. Yep. So there are parts that end with ABC blank will fall here. The score of ABC blank will fall here. The score of ABC would fall here. Yeah. So just to, because we'll be using them in the algorithm walkthrough. So the first point, the first step is to initialize the part, like I mentioned. So we would initialize parts. Okay, so if you look at this, basically the parts we have are, don't forget our symbols, like I said, from this symmetry are just these three, right? So that's what we'll be dealing with. So we have just these three symbols, the blank, the S1, and symbol 2, S2. So you don't need to worry about this right now. I mean, this was just from the previous slide. We just want to highlight that these are what you'll be working with. So now the first function, it takes in a symbol set and it takes in our y, which is our symbol at time step 1. Because don't forget, like it's here, time step 1. And don't forget, we're just trying to initialize the part to do our other operations. And this is actually looping from t to 1 to t. So of course, you know that it's time step 1 or time step 0. If it's 0 indexed, so we'll just use time step 0. So that's what's going to be our y here, and we have these buckets that would store data. Yeah. Okay, so let's first go through this. So we have this list called initial. First of all, our path would be set to null. The appropriate thing to use might not be null, because like I said, this is just a pseudocode and not not a particular language, right? So the first thing to see is our path is none. It could be a blank or anything here. So it's none. So what happens is at time t equals 1, which is the first time, you basically update the parts here. So initial blank part score, right? So you update these parts here with the corresponding probability here, right? Don't forget our y's are wise of probability, like list of probability, right? So you basically update it with the score for this. So the score of blank exactly at time t equals, in this case we are saying 1, but if it's a proper implementation and maybe not MATLAB, we would say 0 because 0 index. Then we just initialize the initial part with blank to our part here, and that's for that. And after doing this, you will find out that because you've added our part, which is an initial blank, you've initialized it with this. So our container now, this container here now has just blank, right? And nothing else. So now for the rest of the symbols, what do you do? So don't forget, this is just blank, right? We still have other symbols like R. Yeah, we still have the rest. We still have all these symbols. We just did for blank. So what happens is, okay, so for the rest of these, we just initialize them. So our part in this first case will be all the symbols for each of these symbols. Then we'll update the score for this part. Now you can see we are using initial part score and not initial blank part score because, like I said, this would store symbols, parts that end with symbols. This would store parts that end with blanks. So that's why we're using this. So we're actually updating the parts for the initial score. We're updating it with the subsequent probability score for that particular symbol at this time step, of course. Then what we are doing is the initial part with blank, because we already have, the initial part with blank symbol would be a set addition because we don't want to repeat addition of parts, right? If you have multiple parts, we don't want to repeat. So it's going to be a set addition of this. And as you must have observed, this is looping through all the symbols. Don't forget the symbols that's coming in here, like we said initially, doesn't contain a blank. So it makes sense to have S1 and S2 as part of this. Yeah, so that's why we actually have this. The next part would be pruning, but like you can see here, we would visit pruning later because I think it's just best we talk about the rest of all this before we go back to pruning, because so that it actually makes more sense if we talk about this other part before pruning. So we would just go to pruning. We'll just go straight to extend the parts with blank, this function here. So would be, of course, we're not looping from, we're looping from 1 now, so everything here changes. And now we are extending our part with blank. And if you can see, we have, don't forget our graph, we have S1, we have a blank, right? Going into, like, transitioning into a blank in the next time step, right? We have S1 going into a blank. So if you look at here, this is a blank. We have S1. So we have an edge from S1 to a blank, right? We have another one from S2 to a blank. So basically, we're extending everything with blank. We're trying to, like, in the tree, we're trying to, like, I don't use one mapping, but we're trying to, like, connect them with blanks. So that's basically what extending with blanks mean. And this is basically the whole algorithm that we would walk through now. So extending with blank, we have updated parts with terminal blank. Don't forget, initially we calculated parts that had blanks from, when we initialized everything. So basically we have an updated one, and we also have an updated blank part score. So let's work with that. It's another blank. This is this. Okay, so for parts with terminal blank, now the point is we don't, so repeating a blank doesn't change this symbol sequence. So let's say you have ABC as your part with terminal blank. Of course, part with terminal blank would say ABC blank. Yeah. So, I mean, ABC blank, adding another blank to ABC blank doesn't make any sense, because at the end of the day, everything would be merged together. And of course, ABC and ABC blank would still end up being the same thing, right? So because of that, we actually don't just update for everything. We just like have to make sure that if sorry, if okay, yeah, so it's just like a set addition, right? Just to make sure that you're not doing like repeated blanks, right? You're not, because it said repeated blanks doesn't change the symbol sequence. So if you have this would be like ABC blank. So ABC blank doesn't change. So adding another blank to ABC blank would not change anything. The symbol is still ABC. So that's why we don't add, and that's why we have this set addition here. Then what we do is we update the score for this particular part. So now don't forget that we have updated blank part score, because we're working with parts that has blank. So basically, so we have this, and we are actually taking, so we are updating this in this data structure here, but we are taking the parts from a blank part score. Don't forget, this blank part score was computed like initially from subsequent steps what we talked about. So this part would would most definitely be found in this data structure, in this list or something. So we just pick it, then multiply it by, so we update the score. Yeah, we update it. So even if the sequence doesn't change, so because we are not updating, so let's imagine we are not updating, we're not adding a particular blank here. So even if the sequence doesn't change, the score changes, because theoretically, or not even theoretically, like ideally we've added a blank, but we just didn't update this, right? So definitely the score changed. So that's why we are still multiplying it by um, the probability of blank. And don't forget, we are extending with blank here. So that's why we're working with blanks. Same for these. Now we're extending the parts with terminal symbols. I think there is, I'll come back to that definitely on subsequent slides. But I'm trying to see transition from black lines to black lines. So these are all just going from blank to blank to blank to blank. Okay, well, let's go to the next part of the extend with blank, which is this part. So now we've done for the part that has terminal blank, right? So now we want to do for parts with terminal symbol. These are parts that actually end with symbol and not blanks. So if the part, so if we actually have parts here, don't forget we've omitted this from here. So so if there's a part in updated part with terminal blank, what we do is we just update that particular score. So we update that particular path with this score here. And so you can see that because it's here, so we add, because we already have something inside. So we add. But now another thing to point out here is we're not using blank part score here. We're actually using part score, because this part is actually going to be in our part score, because part score is a result of, actually contains scores that actually contains scores for parts with terminal symbols. So that's why we would use it. And it was different for here. Here, blank part score contains scores with parts that end with blank, and that's why we're using it here. Um, so that's why we're actually multiplying, we're updating it by the part score. We're getting it from the part score. And if the part is not in this place, what do? We basically just add it to our container, then we update the part. Same thing as we did here. The difference is just here we update. And this is actually how to extend our symbols or our parts with blanks. So that's for the second one. So the second one, you can see we're extending. Okay, let me see. Okay, so it's S1 to blank, S1 to blank, S2 to blank, S1 to blank, blank, blank. Okay, so these are still blank, so we ignore for now. So the next is extending with symbols, but like usual, is there any question for extending with blanks before I move to extension with symbols?
Hey Charles, I think Vishen has a question about beam search. He's almost correct, but probably needs a little more explanation. Vishen, can you ask
Oh,
the question? Uh,
Yeah, so I was just trying to confirm. So first of all, the whole objective is just to approximate the joint probability, right? So basically from y1 to yn given input, then you can decompose this into like probability of y1 given input, and then times probability of input y1 given input y1, you try and find y2, and in each round basically you
exactly.
choose top three. I mean, given k equal to 3, so something like that.
Yeah,
Is that
yeah,
what we're trying to
exactly.
do? Okay, and
Yeah,
then
basically.
so basically, if like let's see, so if we set k equals to 3, for example, then the first round we choose top 3. Then in the second round, do we choose 9 or choose 3?
We choose 3. We always choose 3 at every steps. At every step.
Oh,
so the thing is
Yeah.
that if, let's say we have 10 possibilities or 10 logits at each time step. So we choose 3 in the first time step. Then we calculate the product of all of those 10 with the previous 3. So now we have 30. Out of those 30, we choose 3. And then so on. Does that make sense?
where's the 10 comes from?
I mean, like assuming that we have a vocabulary size of 10.
Oh yeah, that makes sense. Yeah.
Okay.
Yeah.
But is it beneficial to choose like a different number of like k from different layers? Because like this is exponential growing, right? So if we choose the fixed number from each layer, is it?
Okay, so first of all, with pruning, it won't grow exponentially because we are pruning. So we're cutting down some. I mean, just imagine a vocabulary size of 10, you're choosing 3, right? So automatically you've cut. So so if you look at it, how many possibilities have you cut? You have a vocabulary size of 10 and you have a k of 3. So you cut 7 in the first time step. And not just 7, you've cut 7 times 10 because initially those 7 will actually like would actually like expand to 10 for each. Don't forget, I said for each of the symbol, we would consider like the whole possible combination in the vocabulary. So if we have like I love deep learning class, in the first instance we have I love deep learning class, and what happens is we are choosing a k of 2. So let's say let's say our 2 marks are love deep learning, right? So now we've cut class, right? So we didn't just cut class. What happened? And we didn't just prune class or take away class. What happened? We've actually cut down that tree. So I was supposed to map out to I love deep learning class. Then that is in the next time step. Then love was supposed to map out to I love deep learning class. So that's 20. I'm sorry, that's 4 plus 4,
No,
8,
I
right?
think I got the point. Yeah, that makes sense.
Exactly. So yeah.
Yeah, thank
So
you.
that's the point. Is that all?
Yeah.
Okay. So let me go to extend. So now we extend with symbols. Um, so it's almost similar to extending with blanks. So like this, you see that um, as a blank like is more like a blank is being extended to S1. So if you look at this tick bars here. So we have a blank extending to S1. We have a blank extending to S2. We have S2 extending to um, S S1 extending to S2, then we have S2 extending to S1. So basically, and the next step you can see it is also extending to a particular symbol. So you can see that this part are actually ending with blanks, and I mean ending with symbols and not ending with blanks like the previous graph. So this is actually the same. This is actually the full pseudocode, but of course would go over them one by one. So we have extension with symbols, and first of all, okay, so for parts that are in parts with terminal blank, so parts that end with blank, what do? We have, so for this part, so for every symbol in our symbol set, we create a new part and we add C to our part. So I don't know if this is actually a big question. Maybe it's the whole concept is still taking time to grasp. But does anyone mind telling me why we actually do this, or why we can actually add a C to? So first of all, what if C? So what if our part was ABC, and what if, and now let's say okay, let's say our part was ABCD, and let's say our C was actually D. But what we are saying now, we are adding ABC to Z, and we said we don't want repetition. So can someone tell me why we are actually doing this? Okay,
Because we already have
so
blanks.
exactly, yeah. So so basically, because we already have blanks. So don't forget I said with blanks, you can actually do what? You can actually extend, right? You can actually extend here. So this is not a repetition, this is an extension because this part has blank. So this is like SUN, right? We're trying to like decode SUNNY. So this is SUN blank, right? And this C is actually a new N. So I'm just giving an example, right? So our part in this case, for example, would be SUN blank, and here will be N. So you can see that we can actually add this because this has a blank already. So it makes sense to add, so it makes sense to extend and not to repeat. So because we constructed a new part by adding this part, so we just update the part with terminal symbol, um, container or dictionary with this new part, right? So after updating, of course, like with everything, we update the parts with the score. And as you can see, we're using blank part score because these parts would definitely be here, right? Will definitely be in part with terminal blank. So it makes sense to get blank here. But this time we're updating it with the symbol because we're extending it with symbols, right? So we are updating it with the probability of that symbol at this particular time steps, this particular time step, t equals 1, as we are working with. So that's basically what we have here. And if you look at this is like the contrary to everything we had here, which would transition from black lines to symbols. Yeah, so this is pretty intuitive. Um, so for the next scenario, what we have is for parts in um, parts with terminal symbol, right? So what we are doing now, just like that particular student answered here, because we have symbols that ending with symbols, so we have to be very careful what we are adding, right? Because they end with symbol. If you have ABC, we don't want to have ABCC, right? Or if you're having SUN, we don't want to have SUNN, because at the end of the day, when we are merging, double N will collapse to 1. But if you have N, a blank, and an N, the blank will just go, double N will remain, right? So that's why we're having this if condition. So if the current symbol is the same as the last symbol in our part, we just take the part. We don't add anything. We just basically take the part. But if not, then what do? We just add like we did here. So that's basically why we have this condition. Then if our new part is an updated part with terminal symbol, we update the score of the new part with this. Now, and don't forget, we're choosing parts with part score because we are working with parts that actually end with symbol. So we're using the part score list or dictionary, or yeah. And we are multiplying, so we're actually updating the score by this. We're multiplying it by this. And so, but if it's not there, what do we do? As we've been doing before, we create a new one by adding it to our dictionary or our set here. So it says the set addition. We add it here, and what do? Same thing. We actually update the score of this new part by using the part score and multiplying it by this. So this is actually extending with symbols. Does anyone have any question before I go on? So I think
Yes.
we've taken. Okay, just go on.
So I'm just so by looking at the code, I'm just wondering whether we can merge the addition of a new symbol by for the case with terminal blanks and with terminal symbols. Since in both cases, if the new symbol is the same as the terminal symbol, we multiply by the probability, but we do not add it to the past because it's already the last one. But if they're different, we add it. So can we combine these two operations together?
You mean, sorry, let me just go on. So you mean, so when you say combine, what do you mean? Because I'm actually mixing with, okay, just go on.
Yeah, I mean, instead of writing two for loops, so you use a single for loop. So you store all the paths, and then you extend. I try to extend by the symbol set, which includes the blank. So then you check if use the logic on the later part. So if the new symbol is at the end, we do not extend, but we still need to multiply by the score.
Okay, so there are two things I would point out. One would be, I don't know, so it's raining here. I don't know if it's disturbing, if it's okay. I could just.
It's okay.
Okay, just give me a minute. Let me just make sure. Sorry. So okay, let me go on. Okay, so first of all is one, we are looping through two different things, right? So in the first case, we're actually looping through parts with terminal blank. So this part that are here would actually be parts that has terminal blank and not this part, right? So these parts here are actually from this container that says parts with terminal symbol. So parts with terminal symbol would have a different kind of part from this one. So that's one reason why you would want to have two for loops. Second reason why you want to have two for loop is just from a computational or time complexity point of view. We might be doing some larger complexity in terms of O of n or O of whatever complexity we're talking about. Does that answer the question?
I say kind of, because we can still combine the two containers or two lists, right? The pass with terminal blank and pass with terminal symbol. We can combine this into a single list and then loop through. The only optimization I can see is that probably for the pass with terminal blank, we do not need to create a new pass because we know that pass already exists.
I see. I think that's actually a very nice question. You could try it. This will actually be given to you for homework 3 part 1. So I think it's something you can play with, right? This exact problem, what exactly we are going through, would be given as one of the sections for homework 3 part 1. So I think it's it's also worth trying if you want to combine both containers or both lists. You can actually try it. Yeah, but
I see.
because of time,
I'm interested to understand what are the implications. I mean, if or
oh,
whether
okay,
it leads to
implications of
incorrect results.
okay, so let me take time to think about it. So we have parts here that ends with blank, and we have parts here that ends with symbols. So you're saying that we join these two together, right? And just do one for loop.
Yeah.
Okay. So if this contains so let me see, A, B, C, blank, this contains B, C, B, D, E. I'm trying to say for symbol this. So if a new symbol set, so if our part okay, so I can actually think about this true, but I don't want to I mean, I don't know how we have to manage as regards time, but this will be something I'll have to like sit down and of course
Sure, no problem. Or
think
maybe I
through
can try
to be able to see if it's
try the homework.
yeah, exactly, yeah. I mean, it's actually valid. What you said is actually valid, and it could be that merging them together would actually be okay, depending on your algorithm. But I can't answer for straight right now because I don't know if something is going to change here or break when you're doing it. So basically, I think it's best we try to understand what we're trying to do, basically, so that we don't. Okay, so and that's for extending with symbol. And now we can come back to pruning. So we're returning to this pruning. So what does pruning do? Pruning returns, it deletes unpromising parts from contention to reduce competition. So I think I explained that already. Unpromising parts are parts with lower probabilities, and of course, it's reducing competition because we are pruning down a whole tree, right? So okay, let's not spend too much time here. So basically, this is the whole algorithm for pruning, and it's pretty straightforward actually. But we'll just go through them one by one. So pruning takes in these part with terminal blank, part with terminal symbol, our black parts code that we always update, or I mean, that we have, our parts code that we have. So and a beam width. So you can see it takes a beam width so that we know what we're trying to cut down, right? So our first step is to get out the relevant score. So for all the parts with terminal blank, we get, what do? We actually get all the scores, right? So we store them in a scores list. So parts with terminal blank core, we get them from here, get them from these parts, blank part core. We do the same thing for these, but in this case, we actually get them from part score because this part actually ends with symbol. So we store them in just one list. So that gives us like a list of all the relevant score, right? That matters. So now what do we want to do? We want to prune, we want to get like a cutoff. So first thing we do is to sort the list in descending order because of this computation here. But basically our cutoff is just a beam width that would be working with, I think it's somewhere here. I'll get symbols from both symbols somewhere here. Yeah. So first of all, you sort the scores, then you find the largest score, then you find the cutoff score. Basically, the cutoff score is the kth largest score, right? So the cutoff score would be the third largest score here. So you see sort of sort and find cutoff score that retains exactly beam width part. So that's what this part does. And so just a cutoff. So let's go to this block. So now we found the cutoff. What we are saying now is for parts with terminal blank, if our score, our black part score for this particular P part, if it's greater than or equal to the cutoff, what do? We actually keep it, right? Because that's what we are looking for. We're looking for K something higher. I mean, we're looking for values that are higher than, we're looking for the kth largest probability. Yeah. So if it's greater, we actually keep it. So we keep it here and we update this with the part score, right? So the blank part score for P. Actually, so basically this is what we do. We keep it here, and that's just because if it's greater. The next thing, similarly, for the part with terminal symbol, if our part P, don't forget we're using this because it's with terminal symbol. If it's greater than the cutoff, then of course what we just do is to keep it, then keep the score also, like prone part score, set it to the score for this just because it's here. Then we return all this. And this is just the graph to show. So you retain nodes on the black rows with score above cutoff. So basically these are scores above cutoff. Then what do? You effectively prune out nodes on black rows with scores below cutoff. So basically let's imagine or let's assume this part has scores with low cutoff. We just prune them out. Similarly with this, right? So they will subsequently not contribute to the computation as you must have observed. The last part is what I've explained already for terminal symbols. For the ones that are greater than the cutoff, then you just keep them and you just keep the score also here. And the final thing I would like to mention would be, okay, we've talked about this already for pruning. So, okay, one question before that is, why are we pruning here and not at the end of the loop? And this is actually a very valid question because why don't we just do this, then prune? Why do we have to prune? Because okay, let's imagine we prune here. This will give us something. This will give us a new computation. This will give us another computation. And why do we have? Because I mean, if you prune here, you've already pruned the one from the last time step, right? For this current time step, you won't prune the output of this computation. So, and it's because we don't want to prune parts at the final time step, and it's just because it loses some information. So instead, at the final time step, we just merge parts that represent the same symbol sequence, right? So at the final time step, what do? So at the final time step, this prunes from the previous time steps. Then what do? This is a new computation at the final time step. We extend with blank, and we also extend with symbols at the final time step. But now this is the end of the time. This is the end of this sequence. We are not going back to prune. So what do? So that's why we said here that we just merge, right? And that's why we have this here. So basically, what do? We merge identical parts differing by the final blank. So we have ABC blank and we have ABC. Basically, we just merge the probability for both of them. And that's basically what merge identical part does. And like you can see here, yes, we have S2 blank, and here we have S2. So these are the output of our last time step, right? So we have S2 blank and we have S2. So basically, what do? The merge function just merges both of them together, merges the probability together. Similarly, we have S1 blank and we have S1. So we just merge both together also. And this is just the function for that. So we say if P for part with terminal blank, if P is actually in the merge part, what do? Our final part score, which is what we are looking for, will just be an updated version, because if P is here, we'll just add this to it. So we just add the blank part score of P. If it's not in this merged part, what do? We just add it, then of course update it. Then it gives us our result. And the last part is, because we've been pruning and we're merging, it's very easy at the last time step to just do what? To just pick the argmax of the final part score, right? So this will just give us, so pick the maximum of the final part. So this will actually find the part with the best score. So this is actually the end of the recitation for the pseudocode. If there's any question before I quickly move to, I don't know, I don't know, actually, would there be time for me to like move to the coding part? Just a small run through.
I don't know. We're already over time, so
Yeah, we're already over time. Yeah. But that is actually not okay. Maybe what we'll do is there'll definitely be a boot camp, definitely for homework 3. So we can actually just go through it there. Yeah. So I don't know if there's any question. Okay. So
I also have a simple question.
Okay.
So basically, if we do not prune at the end of the loop, that's so we will actually have at the end of the loop we'll actually have more number of entries than the specified number, right? So if we specify the number of the path to keep is 30, so then the final result will actually have 30 times the number of symbols. I mean, all possible combinations.
Yeah.
Got it.
Yeah, because basically because we didn't prune at that last part, so we just do that. So and like you said, because I mean, like the slide said, we actually don't do that because of information loss. At that point, we find out that if we prune, we'll actually be losing so many information. And a practical advice is your beam width should not be too small and should not be too big, because if your beam width is too big, you find out you're exploding the graph again. You're actually extending the graph. To make it computationally expensive. So we don't want beam sizes that are actually too large and too big. But it's an hyperparameter, so it's something you would play with. There's no one size fit all beam width. There are always, I mean, research would always recommend beam width, and I think when we get to practical implementation of beam search, it will be easy to see or to know what beam width to use. But it's just like an overview, like an overall recommendation.
So you stop at like each like all of the branch have the n tokens, right? Basically.
Yeah.
Okay. How do you like normalize the scores in?
So for normalization, let me see.
Like for example, if one stop at the first branch, then that's definitely have a higher score compared to one that ends after like 10 branches, right?
Okay, so one thing is if I get what you mean by normalization correctly, we are dealing with log probabilities. So everything about CTC works with log probabilities, right? So we're not working with normal probabilities that we're trying to sum up to 1. So CTC itself understands log probabilities. So that's why, first of all, from our model, we are taking the log probabilities from our model, from our network. Then we are passing it to CTC loss itself during training. Then during inference, we're also bringing out log probabilities and passing it to our beam decoder. So when it comes to normalization, I don't really see a need.
Oh, I might join late, like for the CTC part, but like, so basically, the top score at the very end could stop at different like timestamp or like depths, right? So for example, one could stop at T3, one could stop at T5, right?
Okay, so you're saying one could stop at T3, one could stop at T5. So are you trying to ask when we stop?
Yeah, you stop when it's predict the end tokens, basically, right?
Yeah, so you basically you stop when, so if it's like a speech to text, you have an EOS, right? An end of string, end of end of sentence.
Yeah,
So
and then and then the joint probability is a product, right? Product of the conditional probability.
Yeah, so everything
And
has a
then
tree.
if you have T5 stamps, right, and then probability is always smaller than 1, then product will be smaller than T3, right? If not, I'm now missing something here.
No, right. You can do something as simple as normalizing by the length of the string, length of the um, generated string as you reach
Oh, so just
an
divide by
end of
like
sentence.
the length of it?
Yeah, that's the simplest thing that people, and that's very common to do.
Okay.
Normalize by the total length of number of tokens in the string, predicted string.
Okay, that makes sense. And sorry, I wasn't paying too much attention for the previous coding part, but like, do we when we improve, like, is it possible that all of this top like scores or whatever, like, is only in one branch? Like, for example, after the first layer, then we output, like, let's say the K or like beam score equals to 3, and then we output 3 branch. Is possible all of the top scores is only in one branch? That's possible, right?
Yeah, it is very possible.
Okay, that makes sense. Thank you.
Okay, so any other question? We are far above time. Okay, so if there is no question, thank you all for coming, and I hope the recitation makes sense and would definitely help you understand CTC and beam decoding overall. And for your homework 3, part 1 and part 2, you can actually use your implementation for CTC and understand CTC. So thank you very much. So I think Akshat, you can stop the recording.
Yeah. Mm,
Okay. Thank you, Akshat. Thank you very much for
yeah. Thank you.
taking time.
Bye.